Scientists have found evidence of water forming surprisingly close to the most extreme object in our galaxy. Not on a planet. Not inside an ocean. But in material surrounding a dying star near the supermassive black hole, at the heart of the Milky Way. And the closer astronomers looked, the stranger the discovery became. Because this star is only about 0.55 light-years from Sagittarius A*, the supermassive black hole at the center of our galaxy. In cosmic terms, that is remarkably close. Sagittarius A* contains roughly 4 million times the mass of our Sun, compressed into an extraordinarily compact region. And around it is one of the most hostile environments in the Milky Way. Powerful gravity dominates the region. Stars race around the black hole at incredible speeds. Gas and dust are exposed to intense radiation. And enormous amounts of energy move through the galactic center. For molecules, this should be a terrible place to survive. Radiation can break apart chemical bonds. Extreme temperatures can destroy delicate molecular structures. And violent stellar winds can sweep material away into space. So astronomers had a fascinating question. Can stars living this close to a supermassive black hole still create and release the ingredients needed to build new cosmic material? The James Webb Space Telescope has now provided an extraordinary clue. The star at the center of this story is called IRS-3. IRS-3 is not a young star like our Sun. It is an evolved star approaching the later stages of its life. Stars at this stage can become enormous, cool, and extremely luminous. And they begin losing material through powerful stellar winds. Gas escapes from the surface of the star and expands into the surrounding space. That material can contain elements and compounds that eventually become part of cosmic dust and molecules. Stars like IRS-3 therefore play an important role in the cosmic recycling system. They take material that has been processed inside a star and return it to the surrounding galaxy. Eventually, that material can become part of new clouds, new stars, and potentially new planetary systems. But IRS-3 has an unusual location. It is only about 0.55 light-years from Sagittarius A star. To understand how close that really is, imagine shrinking the enormous region around the Milky Way's central black hole down to something we could explore. IRS-3 would be sitting surprisingly close to the gravitational heart of the galaxy. And that makes its existence particularly interesting. The question isn't simply whether the star can survive. The question is whether the material it throws into space can survive with it. That's where the James Webb Space Telescope becomes incredibly important. Webb doesn't observe the universe exactly the way our eyes do. It specializes in infrared light. And infrared observations are particularly useful for studying cool, dust, and molecular material hidden inside crowded cosmic environments. One of Webb's most important instruments for this investigation is MIRI, the mid-infrared instrument. MIRI allows astronomers to examine the infrared fingerprints of material surrounding distant stars. And the center of the Milky Way is an incredibly complicated place to observe. Thousands of stars are packed into a relatively small region. Gas and dust weave between them. Radiation fills the environment. And the black hole sits at the center of it all. In ordinary visible light observations, much of that complexity can become difficult to separate. But infrared light provides another way of looking. Webb can reveal structures and chemical signatures that would otherwise remain hidden. When astronomers pointed Webb toward IRS-3, they didn't simply see a bright star. They saw an enormous envelope of material surrounding it. The star was embedded inside a vast shell of dust and gas. And the details of that shell contained an important chemical clue. Webb detected strong infrared signatures associated with oxygen-rich silicate dust. Silicates are materials containing silicon and oxygen. They are important components of cosmic dust and are found throughout the universe. But there was a problem. Previous observations had suggested that IRS-3 might have a different chemical identity. Webb's continuous mid-infrared spectrum gave astronomers a much clearer fingerprint. Instead of simply guessing what the star was made of from isolated observations, scientists could examine a much more complete infrared signature. And that changed the picture. IRS-3 appears to be an oxygen-rich evolved star undergoing intense mass loss. It is actively enriching the space around it with newly formed material. But then another fingerprint appeared. Water. Not an ocean. Not liquid water floating beside a black hole. And certainly not a hidden planet covered in water. The discovery is much more subtle. Webb detected evidence of water within the envelope of material surrounding IRS-3. Astronomers identified infrared signatures consistent with water molecules in that surrounding material. And that is fascinating because water is a molecule. It is chemistry. It requires particular physical conditions to form and survive. Near a supermassive black hole, those conditions can be difficult to maintain. So how is the water surviving? The answer appears to involve the structure of the material surrounding the star. IRS-3 is continuously losing material through stellar winds. That creates layers of gas and dust around the star. And those layers are not all the same. Close to the star, temperatures can be extremely high. Farther away, the material becomes much cooler. Webb observations and stellar modeling indicate a layered, shell-like envelope extending roughly 10,000 astronomical units from the star. Near the star, temperatures can reach approximately 1200 Kelvin. Farther out, the temperature can fall toward roughly 100 Kelvin. That creates a complicated chemical environment. Different molecules can exist at different distances. Different materials can condense. And dust can provide additional protection from radiation. This is one of the most important ideas in the entire story. Dust isn't simply cosmic debris. Dust can change the chemistry of its environment. It can absorb and scatter radiation. It can create regions where molecules have a better chance of surviving. And around IRS-3, enormous quantities of material are being continuously produced and expelled. The star is effectively building a protective chemical environment around itself. Meanwhile, Sagittarius A* continues to dominate the larger region with its immense gravity and energetic environment. The result is a remarkable cosmic balancing act. A dying star is producing material. Radiation is trying to alter that material. Dust is absorbing some of the radiation. Molecules are forming and surviving inside the surrounding envelope. And all of this is happening incredibly close to a supermassive black hole. But there is something even more interesting about this discovery. It tells us something about how galaxies recycle matter. Stars are not just objects that shine. They are enormous chemical factories. Inside stars, nuclear reactions create heavier elements from lighter ones. Over time, stars accumulate and process these elements. And when stars reach later stages of their lives, they can return some of that material to space. Stellar winds can carry gas away. Later, explosions or other forms of stellar mass loss can distribute even more material throughout the galaxy. That material becomes part of the raw ingredients for future generations of stars. And potentially, planets. This means that the death of one star can contribute to the birth of another. The universe is constantly recycling matter. Atoms that once belonged to an ancient star can eventually become part of another star. Or a planet. Or an asteroid. Or a molecule drifting through an interstellar cloud. The material around IRS-3 is another example of that enormous cosmic recycling system. But this time, the recycling is happening in one of the harshest environments in the Milky Way. The center of our galaxy is not an empty black void. It is an incredibly crowded ecosystem. Stars orbit Sagittarius A star. Gas clouds move through the region. Dust absorbs and scatters radiation. Magnetic fields shape the surrounding environment. And the gravitational influence of the black hole affects everything nearby. Some stars orbit the black hole at extraordinary speeds. Others lose material through powerful stellar winds. And some of that material becomes dust and molecules. Webb is showing astronomers that even this violent environment contains surprisingly complex chemistry. That is an important shift in perspective. We often imagine a black hole as something that simply destroys everything around it. And in some circumstances, black holes can certainly be destructive. But a supermassive black hole is also part of a much larger galactic ecosystem. It interacts with stars. It interacts with gas. It interacts with dust. And the surrounding environment can continue producing new material even while the black hole dominates the gravitational center. IRS-3 is a perfect example. The star is approaching the end of its life. It is losing mass. That mass is spreading outward. And inside that material, chemistry is continuing. Dust is forming. Molecules are surviving. And now water has been detected. That doesn't mean the environment is peaceful. Quite the opposite. The environment is extreme. But extreme does not always mean chemically sterile. And that may be one of the most interesting lessons from the Webb observation. The universe can be hostile and chemically active at the same time. Something else is important here. Scientists did not directly photograph individual water molecules floating around IRS-3. Instead, they detected the chemical fingerprints left by those molecules in infrared light. This is how much of astronomy works. We cannot travel to these stars. We cannot collect samples. We cannot put a thermometer next to IRS-3. Instead, we study light. Light carries information. Its wavelength can reveal temperature. Its spectral features can reveal chemical composition. Its movement can reveal velocity. And its intensity can reveal how much material may be present. Every spectrum is therefore like a fingerprint. Webb's infrared instruments allow astronomers to read those fingerprints in extraordinary detail. In the case of IRS-3, those fingerprints revealed something unexpected. The star's surrounding material contains oxygen-rich silicate dust. And it contains evidence of water. That combination gives scientists a much clearer picture of what is happening around this evolved star. It also raises a bigger question. How common could this process be? IRS-3 is only one star. But there are many evolved stars throughout the Milky Way. And many galaxies contain supermassive black holes at their centers. If evolved stars can continue producing dust and molecular material in such harsh environments, then galactic centers may be chemically richer than astronomers previously assumed. That could matter for understanding how galaxies evolve. Galaxies are not static collections of stars. They are dynamic systems. Stars are born. Stars age. Stars die. Gas moves. Dust forms. Black holes grow. And material constantly circulates. The center of a galaxy can therefore influence its surroundings in complicated ways. And Webb is giving astronomers the ability to study those processes in much greater detail. There is another question that naturally comes to mind. Does water near a black hole have anything to do with life? The short answer is, not directly. There is no evidence that life exists near Sagittarius A because of this discovery. And the discovery does not mean that water is sitting on a planet beside the black hole. But water is an important molecule. It is one of the chemicals we associate with planetary environments, and the chemistry relevant to life. So finding water in unexpected places tells us something useful about how resilient molecular chemistry can be. It shows that molecules can survive in environments that initially seem incredibly hostile. And it suggests that the ingredients needed for future chemistry may be distributed through galaxies in more complicated ways than we once imagined. The water around IRS-3 is part of a much larger cosmic cycle. A star forms. It processes elements. It ages. It loses material. Dust and molecules enter the surrounding environment. That material mixes with other gas and dust. Eventually, some of it can become part of another generation of stars and planetary systems. The universe does not simply create and destroy. It recycles. And that is where this story becomes bigger than a single star. The discovery is not really about finding water near a black hole. It is about discovering that a dying star can continue enriching its surroundings even while living next to one of the most extreme objects in the galaxy. It tells us that stars remain chemically productive even under intense radiation. It tells us that dust formation can survive in surprisingly hostile environments. And it tells us that molecular material can exist where we might not have expected it. The Webb observations also demonstrate why infrared astronomy is so powerful. The universe looks different depending on what wavelength you use. Visible light gives us one version. Infrared gives us another. Radio waves reveal another. X-rays reveal another. Each wavelength reveals a different part of the physical story. Webb is especially powerful because it can see infrared signatures from cool dust and molecules while also resolving extremely distant and crowded astronomical environments. In the case of IRS-3, that capability allowed astronomers to reconstruct the structure of its surrounding envelope. The material isn't simply a uniform cloud. It appears to have layers, different temperatures, different chemical conditions, different regions where different processes dominate. That means the star's environment is more like a complex chemical laboratory than a simple cloud of gas. And the black hole is sitting nearby. Imagine the scale of that environment. A star is losing material. That material expands outward. Dust grains form. Molecules appear. Radiation interacts with the shell. And beyond it, the immense gravitational field of Sagittarius A* shapes the larger region. All of this is happening while light from the entire system travels 26,000 years toward us. The photons Webb detects today began their journey before modern civilization existed. Before telescopes existed. Before humans had any idea that a supermassive black hole sat at the center of our galaxy. And now, those ancient photons are telling us something about chemistry near that black hole. That is one of the extraordinary things about astronomy. We don't need to travel there to investigate. The universe brings us evidence in the form of light. And Webb is learning how to read it. There is also a beautiful irony in this discovery. The star IRS-3 is approaching the end of its life. Yet as it dies, it is enriching the space around it. Its material will not simply disappear. Some of its atoms will continue traveling through the galaxy. Some dust grains may eventually become incorporated into other structures. Some molecules may survive. And eventually, some of that material could become part of future stars and planets. The death of a star can therefore become part of the beginning of something else. That is not science fiction. It is one of the fundamental cycles of the universe. And Webb has now shown us that this cycle continues even remarkably close to the Milky Way's central black hole. So what does this discovery actually change? It doesn't overturn Einstein's theory. It doesn't prove that black holes are harmless. It doesn't mean liquid oceans are floating around Sagittarius A star. And it doesn't prove that life can survive next to a black hole. What it does show is more subtle. It shows that the environment around a supermassive black hole can support the formation and survival of dust and molecular material. It shows that evolved stars can continue enriching their surroundings even under intense radiation. And it gives astronomers a new way to understand how chemical elements and molecules circulate through galactic centers. That may sound less dramatic than saying scientists found water beside a black hole. But scientifically, it is far more interesting. Because it changes our picture of what a galactic center can be. A place we might have imagined as dominated by destruction is also a place where matter is being processed and recycled. A dying star is creating new material. Dust is forming. Molecules are surviving. And the galaxy is preparing those ingredients for whatever comes next. The Milky Way is not finished. Its stars are still evolving. Its black hole is still there. Its gas is still moving. Its dust is still forming. And its chemistry is still changing. Webb is allowing us to watch pieces of that process. And IRS-3 is only one example. There are countless other stars in the galactic center waiting to be studied. There are other evolved stars losing material. Other dust shells. Other molecular environments. And other questions we haven't even thought to ask yet. The more powerful our telescopes become, the more complicated the universe appears. Not because the universe is becoming stranger, but because we're finally seeing details that were invisible before. That may be the real lesson of the James Webb Space Telescope. Every time it looks deeper, it doesn't simply give us another beautiful image. It gives us another piece of evidence. And sometimes that evidence changes the question itself. We started by asking whether a star could produce dust so close to a supermassive black hole. Then Webb showed us oxygen-rich silicate dust. Then it revealed water. And suddenly we were asking a much bigger question. How much chemistry can survive in the most extreme environments of a galaxy? The answer appears to be more than we thought. And that is where this story ends. Not with an ocean beside a black hole. Not with aliens. Not with a broken universe. But with something perhaps even more remarkable. A dying star, only about half a light year from the gravitational monster at the heart of our galaxy, is still producing material. That material is forming dust. Molecules are surviving. And water is leaving its fingerprint in the infrared light. The universe is constantly recycling itself. Stars die so that their material can become part of something new. Galaxies evolve. Black holes grow. Dust forms. Molecules survive. And somewhere in that enormous cycle, the ingredients for future worlds are continuously being prepared. Webb has simply given us a closer look. The next time you imagine a black hole, don't imagine only darkness. Imagine the stars around it. Imagine the gas. Imagine the dust. Imagine molecules moving through the radiation. And imagine a dying star quietly enriching the galaxy around it. Because even in one of the most violent places in the Milky Way, the universe is still creating. And that may be the strangest discovery of all.